students. So we have studied about a motional EMF. Okay, when a rod is moving through a magnetic field, okay, if the movement, if it is not parallel to the direction of magnetic field, okay, there are some conditions, everything we have seen. Okay, so if a rod is moving through a magnetic field, okay, with a velocity v, if the length of the rod is L, okay, so we have seen how to calculate the EMF that will be generated in that rod. So the EMF generated will be what? L, length of the rod. So L vector dot what? Velocity vector cross magnetic field vector. So the angle between velocity and magnetic field must not be 0. So if it becomes 0, the angle between velocity and magnetic field, then EMF will be 0. So if they are all mutually perpendicular, then we can write BVL. Okay, directly we can multiply and do. So this thing we have seen. Now suppose if a rod is rotating, then what will be the motional EMF? That is what we are going to see. Okay, so motional EMF, or simply we can say EMF in a rotating rod. In a rotating rod, consider magnetic field, okay, so here there is a rod. Okay, we can consider the magnetic field. Okay, so this rod, if this is of length L, and based on this pivot, okay, based on this pivot, suppose if the rod is turning, just like this, rotation, okay, if it is moving like this, then what is going to be the EMF? See, suppose if the magnetic field is like this, and a rod, this length of this rod, this is perpendicular to magnetic field, and if it is moving with the velocity in this direction, how to calculate the EMF we have seen. Okay, now for this one, how to proceed? So what shall we do? Okay, see, suppose if I consider this point, this will have its velocity in the perpendicular direction. Suppose if it is moving at that instant, the velocity of this point is perpendicular. Now suppose if we consider velocity v, since this is rotation, angular velocity also we will have to consider, right? So what is angular velocity? V is equal to r omega. So velocity is equal to this length into the angular velocity omega. So since v is equal to r omega, if this length is less, velocity will be less. Suppose if I consider another point, here this velocity is going to be more, correct, because this length is more. Then if I consider the last point, here the velocity will be more compared to this point, and here this is going to be what? 0 at the hinge. So in rotational motion basics, we are studying this v is equal to r omega, and this is how its velocity is going to be. Okay, so each point, its velocity is changing. each point its velocity is changing. So what shall we do? We will consider a small distance here. Okay, we will find the EMF for that small distance and we will integrate from this end to this end. Okay, so what I am going to do is I consider a small length here. Okay, so this length is dx and this is situated at a length x from the hinge. Now if I apply this formula, small EMF between these two small points, in between this small distance. Okay, so I can say dE EMF is equal to what? Applying in this formula. Okay, so what about V here? In this case, for this position, what will be V? What will be V? V will be, instead of R, I can say X, and this is omega. R omega instead of X omega. So dE is equal to, so they are mutually perpendicular. While motion, if we consider that instant, velocity is in this direction, magnetic field is in this direction, and length, the displacement is in this direction. So everything is mutually perpendicular. So what I am going to do, okay, instead of V, I am going to write X omega, then I am writing magnetic field. Okay, then what? Distance, this L is nothing but this distance dx. Is it clear? Small EMF between these 2 points is equal to what? BVBL. Instead of L I am taking dx. This is magnetic field B. Instead of velocity I am taking x omega. Now total EMF is going to be what? The sum of all these small EMFs, and here it is going to be omega B. These two will be constants, right? Integral what? X dx. So I will have to take each point like this. From where to where? From 0 to L. So putting the limit 0 to L. So E is going to be what? Here omega B x square by 2, putting the limit 0 to L. So EMF is equal to what? Here if we put the limit, half B omega L square, half B omega L square. So this is going to be the EMF. This is going to be the EMF that is generated between the edge of, or between 2 points in a rotating rod. Clear or what? So EMF in a rotating rod. Please note down. Clear? Pause the screen and note it down. Okay, clear? Okay. And suppose if it is rotating like this, if this is rod, okay, magnetic field is in this direction. If it is rotating in this direction, obviously the velocity direction is this. Okay, now how to find the direction of EMF? Right hand palm rule we were using, same thing we can use. This is the direction of magnetic field, this is the direction of velocity. Now where the palm is facing in this direction. So this is going to be the, whichever direction it is showing, that will be the positive end. Suppose if this is moving in this direction, if it is rotating in this direction, okay, then velocity will be in this direction. If the magnetic field is in this direction, so this is going to be the direction of magnetic field. So here this is going to be the direction of velocity. Palm is showing in that direction. So here the EMF polarity will be in this direction. So if the field is going inside, this is how. If the field is coming out, likewise we need to keep the palm and we need to understand find the direction. Say for example, suppose if it is dot magnetic field, if it is dot magnetic field and this is the rod, if it is moving like this, then this is going to be the direction of velocity. So now this is the direction of magnetic field towards you, and this is the direction of velocity. So this direction is the direction of EMF, positive polarity. So what will happen? This is going to be the situation. Okay, so likewise the direction of EMF can be found. Clear or what? Clear? Okay, shall I erase this? Okay, fine. Suppose if we are getting some other shape, not rod, any arbitrary shape, if we are getting, suppose if this is the magnetic field, if this is the magnetic field, suppose if we are getting the shape of the rotating rod like this, then which one we should take? We should take like this. So this must be the length. This must be the length. Okay, so based on the rotation, consider this as the length, then remaining velocity, magnetic field and all, based on that we can find the EMF, the direction of EMF, everything, I mean polarity, everything can be found. So take the displacement. If the length is any arbitrary length or something else, arc, semicircle, whatever it may be, take the displacement, consider the initial point and final point alone, and we need to solve this. Clear? Fine. So along with this we will have to do some problems in order to understand the concepts well. Okay students? Okay. Hello students. So in this session now we are going to see a few problems on the motional EMF, that too in motional EMF, the motional EMF in a rotating rod. Okay, other cases already we have solved problems. Okay, in this we will see problems on motional EMF in rotating rods. Okay, problems. Okay, so EMF in rotating rods. Okay, so general formula is half BL omega square. Okay, general formula is what? EMF is equal to half BL omega, sorry, B omega L square, half B omega L square. Okay, now how to approach the problems also I have explained. Okay, now in the problems which we are going to do, we may have to do that approach. If simply L is given, just if we need to find EMF, okay, direct substitutions can be done, we can get the answer. But all the problems cannot be solved like that. Okay, so we will see now different questions. Here, this is your first problem. So AB is a conducting rod of length L. C is the midpoint of AB. C is the midpoint of AB. Find VB minus VC. Okay, VB minus VC. So suppose if its length is L, if we try to do direct substitution, half B omega L by 2 all square, if we try to do that, we will be getting an answer. So let us try to see that also. Okay, EMF is equal to, we know this formula, half B omega L square. Now suppose if we try to substitute, okay, fine, B is there, omega is there. Obviously, that this VB minus VC means fine that length will be what, L by 2. So L by 2, the whole square, if we do, half B omega L square by 4. So we will be getting what, 1 by 8 B omega L square. Okay. So let us see. If we look at the option, if we look at the option, this answer is not at all there. Suppose if this answer is there, definitely we will be marking this, correct or what? That will give us a negative mark. Okay, so we should approach in the way we have discussed while discussing the theory part of this. Okay, let me try in that way. Suppose here, uh, magnetic field. Okay, we have the rod. Okay, A, C, B. Okay, now how we derived it? Suppose if this is how it is going to rotate, let us take a small portion dx, small portion dx, and from what length? This is at a length x from the pivot or from the hinge. Okay, or from the point here. Okay, from here we will have to take. Now what is velocity? As we discussed, velocity is always going to be perpendicular, and v is what? V is r omega. In this case we can say v is equal to x omega. Now if we try to substitute, okay, I'll moving to the next page. De, small emf due to that small element dx, this is equal to what? uh, bv, actually E is equal to what? BVL if everything is mutually perpendicular, or otherwise E is equal to L dot V cross B. Okay, if angles are there, definitely we'll have to deal that. Everything is mutually perpendicular here, so BVL. Now in this case, BV into what? BV into dx, we can say. V can be substituted like B into x omega dx, x omega dx. Now total emf is what? The summation or integration of small emf. This is equal to integral what? B omega x dx. So here B omega, they are constant, x dx is the variable thing here. So what will be the limit we should put here? See children, we have to find VB minus VC. So we are interested in the EMF or voltage difference between C and B. So the limit should be what? Limit should be from L by 2 to L. L by 2 to L. Now, if I take this B omega outside and if I integrate, this is going to be x square by 2, putting the limit L by 2 to L. Now, I am going to take this 2 outside, B omega by 2. Instead of x square, I am putting L square minus here, L square by 4. So now this is full minus quarter, L square minus L square by 4. So what this is going to be? B omega by 2 into 3 by 4 L square. So the answer is 3 by 8, 3 by 8 B omega L square. So now this is the answer. Now if we come to the options, the trouble is 3 by 8 B omega L square minus 3 by 8 B omega L square is also there. Okay, how to deal this? The question is like a VB minus VC. Okay, now our right hand palm rule. So this is the direction of magnetic field and this is the direction of motion of rod. So obviously this is going to be the polarity. I mean positive will come in this side. Positive will come in this side. So C will have the positive terminal, correct or what? C will have the positive terminal. So I could say, suppose if this is the rod, if this is the rod, this is B, C, A. Okay, these are magnetic fields, and V is in this direction. So what we got? We got this as the direction of polarity. So when they ask VB minus VC, actually VC is having positive polarity. So we can put here minus, negative. Clear? So minus 3 by 8 B omega L square. Okay. So option D is the correct answer. Clear, all of you? Okay. So the thing is, direct substitution of formula will not work here. Okay, so in those kind of situations, we have to take in the same way, the same approach. Take dx, integrate and proceed. Okay, shall we move to the next problem? Okay, pause the screen and note it down. Okay, clear? Done. Next one. So here, the problem is like a conducting rod AC of length 4L is rotated about point O in a uniform magnetic field B directed into the plane of paper. AO is L, OC is 3L. Now VA minus VC. Okay, so here this is going to be okay. Okay, the pivot, the hinge is coming in between, that is between A and C. So suppose if this is C and this is A, and if the rotation is in this direction, okay, then now I could say that velocity at C will be in which direction? Velocity at C will be in this direction. And what about velocity at A? That will be going down. This will be the direction of velocity at A. Clear or what? Hinge is between A and C. When C goes up, A is going down. Okay, clear? Now, this is the magnetic field. Okay, going into the plane of paper. Okay, now if we try to do, we can take like, suppose if this is the hinge, from O, if this is O, from O to C, this is one segment. This is moving upwards, velocity, magnetic field. Okay, now suppose what is the length of OC? OC is actually 3L. OC is actually 3L. Now, if I need to find the EMF for that particular segment, that is full rod is there, I can directly substitute half B omega L square. I can substitute here the length. So this is going to be what? Half B omega 3L the whole square, and we will be getting half B omega 9L square. 9L square. Or I could say E is equal to 9 by 2 B omega L square. So this is the EMF between O and C. Let it be there. Now next segment is here. So here between A and O, the length is actually L. The length is actually L. So what is the EMF here? I can directly substitute, full segment is there from the hinge, half B omega L square. Okay, so one is half B omega L square, another is 9 by 2 B omega L square. Now suppose if I consider OC, what will be the direction of EMF? I mean the polarity will be. So this is the direction of magnetic field. This is the direction of velocity. This is the direction of the palm. So I could mark the positive terminal like this. Okay, so this is what is CO. Okay, and what about this one? This is the direction of magnetic field. Regarding OA, this is the direction of velocity. So this is the polarity which we will have to keep. So this is how it is going to be. So what is the question? VA minus VC. So if we take VA minus VC, VA minus VC, if we try to do like that, okay, this is nothing but what we have found actually. We have found VO minus VC or VC minus VO and VO minus VA. All these things we have found. So let us take like here, this is actually VO minus VA. This is half B omega L square. Here we can write this is VO minus VC. VO minus VC is actually 9 by 2 B omega L square. VO minus VC. So if we need to solve this, we can take in this way. Okay, both of them putting together. Okay, what we need to find? We need to find VA minus VC. Okay, so VO minus VC. Okay, then minus VO minus VA. Okay, if we take like this, VO minus VC, already we have found VO minus VC 9 by 2 B omega L square minus VO minus VO minus VA. VO minus VA is half B omega L square. Half B omega L square. So if we do this, VO minus VC minus VO plus VA, which is nothing but VA minus VC, this is equal to what? 8 by 2 B omega L square we are getting. 8 by 2 B omega L square. So look at the options. Okay. 8 by 2 B omega L square. So what is that? 4B omega L square. Option A is the correct answer. So this is nothing but 4B omega L square. Clear? So we took the rod, we took the conductor separately between OC and OA. We found the EMF, we found the polarity. After putting the polarity based on the question, we have arranged it, we got the answer. Clear? Fine. So we will move to the next problem. Okay. So this is a wire is in the form of a semicircle of radius r. Okay, one end is attached to an axis about which it rotates with an angular speed omega. The axis is normal to the plane of semicircle. Okay. The wire is immersed in a uniform magnetic field B parallel to the axis. Find the induced EMF between point O and P of the semicircle. Okay, so find the induced EMF between O and P. So they are asking like a VO minus VP. So here EMF is what? Half B omega L square. Which L we should take here? We should take the semicircle length or just diameter. So here comes, we are always interested in the displacement. Okay, that is actually vector. From that only this formula came. So we are interested in the displacement. So half B omega 2R the whole square. 2R the whole square. So half B omega 4R square. 2 will be cancelled off. We will be getting 2b omega r square, 2b omega r square. Now let us see the polarity also. This is the direction of magnetic field. Okay, and the movement will be in which direction? Movement will be in this direction. So this is going to be the velocity is in this direction. This is rotated anti-clockwise. Sorry, clockwise. Rotated clockwise. So this is going to be the direction of velocity. So the positive terminal will come at P. So definitely this is going to be like this. Okay. Now what they have asked, VO minus VP. VO minus VP will be obviously what? Negative then. Okay. VO minus VP. If they are asking VO minus VP, this is going to be negative 2b omega r square. If it is VP minus VO, then 2b omega what? R square. Clear or what? Okay. Okay, so this is here, the velocity is in this direction. Need to be careful regarding the direction. Clear? Shall we move to the next problem? Yeah. So a metal disc of a radius r is equal to 25 centimeter rotates with a constant angular velocity omega is equal to 160 radians per second about its axis. Find the potential difference between center and rim of the disk. If the external uniform magnetic field B is equal to 5 millitesla directed perpendicular to the disk. So this is just like a disk. Okay, so this is magnetic field. Okay, now we have got a disk here. Okay, so disk means this space is completely occupied with the material. Now, if this rotates with an angular velocity omega 160 radians per second, then what they are asking is what is the potential difference? What is the potential difference between the center, and the rim? Rim is this, between the center and the rim of the disk. So what we can take, we can consider a rod here. Okay, between those 2 points, whatever be the potential difference, that is going to be the potential difference throughout the disk between rim and center wherever we take, because they are, this is same node, right? This is same node. So wherever we take between the rim and the center, the potential difference is going to be the same. So we can directly apply this formula. E is equal to what? Half B omega. Instead of L square, we can take here R square. So half into 5 into 10 raised to minus 3 into 160 into, here the radius is 25 centimeter. So 25 by 100, in order to convert into meter, it's square. So if we solve this, we will be getting 25 millivolt. Option B is the correct answer. Clear or what? Okay, so okay children, so this is enough for as a practice for motional EMF in rotating rod case. We have taken some good problems also, how to apply the application of integration. Okay, by integrating certain questions we will have to do like that. Suppose if it is from half to full or between some points, if they ask, definitely we will have to take the limit, initial limit and final limit in that. Okay, likewise we will have to do remaining questions. We can apply the formula half B omega L square. Okay, so practice more questions. Thank you. Goodbye. Good luck.